My name is Philip. I'm a security analyst at Compass, and I'm going to be talking about some products that I came across during my work here. So basically, which products? Basically, I'm going to be talking about products that allow you to log into Windows using only your smartphone, so you don't need to enter a password. And you can imagine, so here's a bit of an illustration. The user sits in front of the computer. The user enters his username. The user gets a notification that basically says, do you want to log in, yes or no, on his smartphone. The user clicks yes, and the user is logged in to the computer, and the user did not need to enter a password. And you can sort of think of this as a new or a modern iteration on the smart card login. And in this talk, I will basically go over 3 products that implement this sort of smartphone passwordless login. And for each of these products, I'm going to show you how the login actually works. So how they actually log you in without a password. And also, I will show off a critical vulnerability for each product that basically allows a low-privileged user to log in as another user by abusing some mechanism of this login. So when I'm talking about passwordless login to Windows, and when you might be thinking of Windows Hello, and you might be wondering in which relation is this, are these products that I'm going to be talking about to Windows Hello. So there's basically 2 big differences. Number one is that all the products that I'm talking about, they are third-party products, and Windows Hello is, of course, from Microsoft itself. And the other big difference is that Windows Hello is really bound to one computer, whereas the smartphone can be used to log into any domain-joined computer. So that's really the big difference. So here's sort of all the involved parties in this passwordless login on these products that I'm talking about. There's the smartphone, there's the server, there's the computer, and then there's the domain controller. Now, the domain controller is in quotes. Why is that? Well, basically, of course, when you log into your computer, to your workstation, you also authenticate yourself to the domain controller, because of course, you want to be able to access the network resources inside the Active Directory Windows network. And this part is actually unchanged, and this is also true when you log in with these products using only your smartphone. And so when you log in without the password with these products, you're also able to access network resources. And so what I'm trying to say is basically that these products don't change the way the Active Directory works, the Active Directory authentication works. So Kerberos and TLM, all these protocols are unchanged, basically. So that's why the domain controller is in quotes, but it's still important. And basically the lines here are just to show how sort of the smartphone is connected to the computer. Now you might be wondering, how do these products, so when these products are installed on a computer, how do they hook themselves into a login process? How do they execute their code when a login process is started? The way this is done is basically these products install a custom credential provider. Now, in the context of the Windows authentication, a credential provider is basically a DLL that is referenced by some registry keys, and Windows looks up these registry keys and then loads the DLL for any login process that is started. And so these products install their own credential provider DLL, and so this way they have their code executing whenever a login process is started. Now, usually these products also install a server on the computer as well, which communicates to a service on the computer, which communicates to the server over HTTPS, and the service communicates to the credential provider DLL over some sort of inter-process communication. Now, what's important about this is that these credential provider DLLs, they don't have the power to actually validate credentials. Their purpose is basically to gather credentials that the user has entered and then pass them to the login process where they will be validated later on. Now, of course, this presents a bit of an issue because, well, the user is not entering his credentials. The user is not entering his password. That's the whole point of these products. But these products run in the context of the credential provider DLL, and so to log in the user, they need valid credentials. And the solution to this is to basically cache valid user credentials and then pass them to the login process. And this is really the main functionality that these products implement, is caching valid user credentials and then unlocking them and passing them to the credential provider DLL once the user has authorized the login on the app. Now, I guess I got lucky because the 3 products that I looked at all cache their credentials at different places. So we have SafeNet, which caches the credentials on the computer, VeridiumAD, which caches them on the server, and HYPR, which caches them on the phone. And this is really sort of the biggest design decision that can be made when these products are built, because this has a huge impact on both the user experience as well as on how these products actually work, and of course, how you would go about attacking these products. So now we're done with the introduction, and we're going to go through now each of these products. I'm going to show you how they log you in without having to enter a password, and show you the vulnerability. So first up is Thales SafeNet. The way it works is for the user has to install the SafeNet app, scans a QR code that he gets from the company, and then that user is basically enrolled for his own user. Now, if that user wants to log into a computer with SafeNet, the user goes up to the computer, enters his username, then that user gets a notification on the phone saying you want to log into this computer with SafeNet, yes or no. The user says yes, or pushes yes. And then the user, if it's the first time that user tries to log into the computer, the user needs to enter his password. Now the user enters his password and the user is logged in. The next time the user tries to log in with SafeNet, the user just has to accept the notification on the phone, and then the user is logged in without having to enter the password. Now you might have an idea of what's going on. Well, basically, when the user logs in the first time and enters his password, the SafeNet credential provider DLL takes that password and basically encrypts it and writes it to a file. So this is what you see here on this slide, is basically the file where the encrypted passwords are stored. Behind those black bars are base 64 strings of the password ciphertext, and this file is just stored in the installation directory. And of course, when you're logging in when a user logs in, and the user basically authorizes the login on the app, saying, yes, I want to log into this computer, the SafeNet credential provider just opens this file, reads out that user's encrypted password, decrypts it, and then passes it to the login process where it is validated, and that user is then logged in. Now, of course, when I was looking at this, I was interested in how these passwords are actually encrypted, because this file is actually readable for all users. So if I find a way to somehow decrypt these ciphertexts, I can get the passwords of other users. So here's sort of the analysis setup. I started a UAC prompt, which is another login process, basically. This runs as the consent.exe process. And below, you can see the credential provider DLL in the loaded DLLs tab. And this DLL is basically the credential provider DLL that was installed by SafeNet. So if I want to see how these passwords are basically decrypted, I just need to basically monitor or see what this DLL is doing. And here you can see a API monitor capture of a login process. Basically, what's marked in red is a call to crypt unprotected data. And below that is a black bar, and this is just the plain text password. And so basically, the passwords are encrypted and decrypted with the Windows Data Protection API. And the Windows Data Protection API is an API by Windows where basically the idea is that only the user that encrypts something can then decrypt that data. So Windows just enforces some access control on the encryption key. This is, for example, used by browsers to encrypt passwords stored in the browser. Now I know how these are basically decrypted, and I want to see how they're encrypted. So I just threw the DLL into Ghidra and searched for references to crypt protect data. And there's one reference which presumably encrypts the passwords. And what can be seen here, what's marked as red, is the flags parameter of this API function. And this is set to 5, and this means that the third bit is set to 1, and that means that the local machine flag is set. And the local machine flag basically voids all the security guarantees I was talking about before, because with this flag set, the encryption key is actually readable for all users on the computer. So any user on the computer can decrypt that data. So now you might be wondering, okay, what's stopping a normal user from just reading this file and decrypting other users' passwords? Well, there's a small complication. SafeNet uses the entropy to encrypt passwords. And this entropy is basically like an encryption password. So if you use crypt protect data with an entropy, you need that same entropy when calling crypt unprotect data. Otherwise, the decryption is going to fail. Now, I logged in a bunch of times and it was always the same value. And it turns out it's just hard-coded into the DLL. So there's this big base64 string in the DLL. And if this is followed from sink to source, it eventually ends up as the entropy parameter in the dpap function calls. Okay, so long story short, what we end up with is basically a vulnerability where normal users on a computer can basically just decrypt the passwords of other users that have logged into this computer with SafeNet. So here's just my PowerShell proof of concept that just takes these base64 ciphertext passwords and decrypts them. And this can be run in any organization for any user. It just has to be that another user has logged into their computer with SafeNet. So this was disclosed to Thales, and they basically tried to fix it, but they failed. So they basically just added another layer of encryption. So now the passwords are not stored in a file anymore, but in an encrypted database. And there's a new DLL that basically manages this encrypted database, but really nothing's changed because everything like the data protection API encryption is still done with local machine. And so basically to exploit this, I wrote a small executable which just imports this DLL. And there's a function exported by this DLL which is called get AD cache creds. And imagine what this does. And so basically same thing again. Now the low privileged user just has to run this executable, which you can see here. Basically, I just ran this executable with a user SID. And if that user SID logged into the computer with SafeNet before, then I get that user's password. And so this is really bad. And you might be wondering what's actually going on. Why is this file with encrypted passwords readable for all users? Why are they using local machine to encrypt? What's going on here? And the reason for this is basically this here. So I didn't state this explicitly before, but these products support passwordless login for both the lock screen, the UAC prompt, and SafeNet is the only one that also supports passwordless login for the run as different user function by Windows, which is the one you see here when you do shift right click. And what's interesting about this is that this login process is actually started. So this login process, this run as different user login process is basically started by the Explorer process. And the Explorer process, of course, runs with normal user permissions. And so the login process runs with normal user permissions. And this means that the credential provider DLL that is loaded, so the SafeNet credential provider DLL that is loaded, runs with normal user permissions. And well, this is the problem because, of course, if you want to support passwordless login for run as different user, then the credential provider DLL running with normal user permissions needs to be able to somehow read and decrypt the passwords of other users. And that's really the root cause of this vulnerability. It's basically vulnerable by design. So if any such passwordless product supports login with run as different user, then it's basically vulnerable by design. And so in the newest version, they added a registry key, which if this is set to 1, then the encryption will not be done anymore with local machine. But, well, it's set to 0 by default, so it's still vulnerable by default, which I think is pretty bad. So if you use the software, please make sure that it's actually set to 1. So this was Thales SafeNet. Let's move on to the next product, VeridiumAD. So for this product, the user again registers, installs the app and registers for his user. Now, if the user wants to log into a domain computer, the user just goes up to the computer, says login with VeridiumAD, enters his username, gets a notification, and the user is logged in. And unlike SafeNet and unlike the product afterwards, VeridiumAD is the only one that does not require the user to sort of enter any login credentials or enter a password at any time to enroll to a computer for passwordless login. So there's no need ever to enter a password. How does it work? Well, basically, when the user enters his username, the VeridiumAD service makes a HTTP request to the VeridiumAD server with that user's security identifier. And the VeridiumAD service also starts basically polling the VeridiumAD server, basically waiting for the user to either accept or decline the login attempt. Now the server is going to trigger a notification on the user's phone, and the user can which is going to say you want to log into this computer, yes or no, and the user accepts. And once the server learns that the user has accepted the login, the server basically returns that user's login certificate as a response to one of those polling requests. The login certificate of that user is then basically passed from the VeridiumAD service to the VeridiumAD credential provider, and the credential provider passes it to the login process where the user is then logged in. Now, I said before that VeridiumAD caches credentials on the server. This is not quite true. It's a bit of an abstraction. Basically, what's going on is that there's this on-premise server that exposes these API endpoints for the computers. And this on-premise server talks to the Active Directory certificate service to basically generate the login certificates of users on demand. But I abstract this to credentials are stored on the server because for all intents and purposes, this is how the workstation or the smartphone sees it. Now, how do we go about attacking this? Well, let's say the attacker is in the internal network. The attacker can talk to the VeridiumAD API endpoint, and the attacker can actually make this request to trigger the login notification for any user. So the attacker can just make this request. This is what you see in the image above. Basically, the attacker just specifies an arbitrary user security identifier, so the target user, and the attacker is also able to specify some text. And then the server basically returns a session ID, and this actually does trigger a push notification for that user. And while the attacker is already talking to the server, so the attacker might as well start polling the server. And if the target user actually accepts this malicious push notification, the attacker is actually able to basically get that user's login certificate. So this is what you see here. On the left is basically the polling request. And since the user has accepted the login, the polling request returns a token. And then this token can be exchanged for the user's login certificate. Now you might be wondering, what can an attacker do if he has the target user's login certificate? And since the attacker in this sort of threat scenario is already in the internal network, the attacker can just basically use this login certificate to request a ticket granting ticket, so Kerberos ticket granting ticket, or with some magic get an NTLM hash of that user. And well, basically now the attacker can authenticate with NTLM or Kerberos to network resources, and basically it's not as sexy as a password, but it's almost the same since the attacker is in the internal network. There's a small complication to this, however. The endpoint that basically triggers the push notification and that is used for polling, this endpoint is protected with an SSL client certificate. And basically, when I was looking at this, I was of course wondering, okay, where does this client certificate come from? And this is where it comes from. Basically, when the VeridiumAD service is installed for the first time or is restarted, this HTTP request is sent to the VeridiumAD server. And what is sent in here is a certificate signing request, which is then, and in the response, the server basically returns the SSL client certificate. And what's good news for the attacker is that basically this endpoint here, this register device endpoint, can be used by any domain user. So it's protected with NTLM authentication, but any domain user can basically make this request and get an SSL client certificate. That can then be used to talk to the API endpoint to trigger login notifications for any users. And so basically, the idea is that the attacker first generates a certificate signing request. So just with OpenSSL, basically just sort of mimics the observed login certificate from the service, authenticates to this certificate signing request HTTPS endpoint, gets the certificate signed, so basically gets the SSL client certificate, triggers push notifications for users, maybe combine it with some social engineering, and then, well, if any users fall for these login notifications, the attacker can basically get these users, this user's login certificate and log in as that user. And what's the issue here? Well, the issue is sort of a chicken and egg problem because, well, VeridiumAD is the only of these products that does not require to sort of enroll to a computer beforehand. But that means that the service running on the computer needs to be able to get login credentials for any user without sort of any prior credentials of that user. And well, this means that you need to have this functionality where with this API endpoint, you know, the service can get any other user's credentials. But then how do you protect this API endpoint? Well, you use the SSL certificate, but then where does this SSL certificate come from? And then you end up at a point where it's basically insecure. The way they fix this is that basically now only computer accounts in a specific group are allowed to talk to this certificate signing request HTTPS endpoint, basically. Now, if the attacker still wants to mount this attack, the attacker first needs to compromise one of those computer accounts, basically. Okay, so next product, next and last, HYPR. Here the user installs the HYPR app, then logs in normally, so just with the password, to a computer, opens the HYPR desktop app and scans a QR code in this desktop app with the HYPR app. And then the user basically gets a button in the HYPR app, a unlock button for, you know, the current user and that computer. And the user can have multiple unlock buttons for different computers and users. And to log in, the user just clicks the unlock button for the desired computer and user, and the user is going to get logged in. The user does not even need to touch the keyboard of the computer to log in. How does it work? Well, basically, the HYPR service, whenever a login process is started, so either the screen is locked or there's a UAC prompt, the HYPR service is polling the HYPR cloud server. Now, the user is going to click the unlock button for that computer, and the HYPR app is going to send some HTTPS requests to the HYPR cloud server to initialize a login flow. Now, just remember, when I said in the beginning, is that HYPR actually caches credentials on the smartphone, and what this means precisely is that the user's login certificate is stored on the smartphone. And so now once a login flow is initialized for that user and that computer, the HYPR app encrypts the stored login, encrypts the login certificate and sends it to this HYPR cloud server. And the HYPR cloud server basically forwards it to the HYPR service on the computer by sending the encrypted login certificate as a response to one of those polling requests. And the HYPR service is going to take this encrypted login certificate, decrypt it, pass it to the HYPR credential provider, and the HYPR credential provider is going to pass it to the login process where it will be validated and the user is going to get logged in. Now, a bit of information about the encryption. So basically the login certificate is encrypted with a key that is derived with Diffie-Hellman between the smartphone or the HYPR app and the computer/HYPR service. And the certificate is basically encrypted by the smartphone and then decrypted by the service during a login flow. And you need to be system on the computer or have full control of the smartphone to decrypt the certificate to have access to the encryption key. And well, this looks pretty safe right now, but there's a crack, which is that it's possible to basically steal encrypted login certificates of other users. And this can then be escalated to login as another user, which I will show later on. So first off, how can an attacker, so basically first off, before I keep going, the attack scenario is basically an attacker that has code execution on a computer with a low privileged user. And there's another user, which I will refer to as the target user. Let's say that user is a local administrator on the same computer that uses HYPR to log into that computer. And the attacker is, of course, looking to log in as that target user. So this is the attack scenario. Now, there's some parameters stored in the registry, which are readable for all users. So for every user that has basically enrolled his app for hyperlogin on the computer, there's a registry key. And in that registry key, there are some parameters. And these parameters can basically be used to communicate to the HYPR cloud server on behalf of that user. And all these registry keys are readable for all users on the computer. So the attacker can basically read out the parameters of the target user. And now the attacker can poll the HYPR cloud server on behalf of the target user. And if the target user, while the attacker is polling, clicks the unlock button for that computer, the attacker is going to be able to get that user's encrypted login certificate, which you can see here basically is the polling HTTPS request, and then in the response marked in red is the encrypted login certificate of the target user. So how is the attacker going to be able to basically leverage an encrypted login certificate to log in as another user? So I will show this. I think it's easier to understand the attack, show the entire attack, and then we'll go through the details. So here's sort of the setup. We have the attacker with code execution on the computer. The attacker has installed the HYPR app on his own smartphone and enrolled his low-privileged user for hyperlogin on the computer. And the attacker has also set up his smartphone to send all the HTTPS traffic of the HYPR app through an HTTPS proxy. Now, of course, the HYPR service is always polling for the user login because the attacker has started a login process. So because the target user is a local administrator, the attacker has started a USC prompt. Now, the attacker is going to click the unlock button for his low-privileged user on the computer. And the app is going to basically start sending these initialization HTTPS requests. And the attacker is going to intercept these and modify the parameters such that at the end of step 2, the HYPR cloud server will basically think that the target user has started a login process, not the attacker user. Once this is done, the HYPR app of the attacker is going to send the attacker's encrypted login certificate. The attacker is going to drop this request and instead send the stolen login certificate that was obtained in the step before. And well, this is going to get forwarded to the HYPR service on the computer. And the HYPR service on the computer will basically decrypt that stolen login certificate for the attacker and then log in the attacker as the target user. So this is how the attacker can basically reuse a stolen encrypted login certificate to log in as another user. There's a complication, unfortunately, which is that the server sets this encryption nonce value, the enc counter. So this basically gets set at the end of step 2, at the end of initialization. This value is sent to the app. The app takes this enc counter value, prepends it to the login certificate, and then encrypts this data. And then this is actually the data blob that is sent encrypted to the HYPR service. And this enc counter value is also sent to the HYPR service by the server in the basically polling response containing the encrypted login certificate. And the HYPR service is going to read that enc counter value and compare it to the enc counter value in the decrypted, received blob. And if these values don't match, the HYPR service is going to abort that login process. And this is, of course, a problem for the attacker because this value is set by the server and it needs to match the static value that was basically obtained when stealing the encrypted login certificate. But the attacker doesn't have a direct way to actually influence this value. Now, fortunately, this value is not like a super random value that is never repeated. It actually starts at 1 and is incremented by 1 for every new login flow. And it is reset back to 1 when a user deregisters from a computer. So basically, the user can click on a button in the app to basically deregister a user-computer combination from his app. And then these registry keys I was talking about earlier will be deleted. And the user is not going to be able to log into that computer with HYPR anymore. When a user deregisters from a computer and then re-registers, what's important is that the enc counter is reset to 1, but the encryption key for the login certificate stays the same. So that's really important. basically the reason for that is because the private and public key parts for the Diffie-Hellman key derivation of the smartphone and of the computer stay the same. So these are basically static for the HYPR app on a smartphone or static for the HYPR workstation on the computer, for the HYPR service on the computer. And basically, now this is the solution to this end counter problem. The attacker can deregisters the target user, waits for the target user to re-register, and then mount this attack with the encryption, with the basically reusing the encrypted login certificate. So just to sort of summarize, here's the full attack. The attacker first obtains the encrypted login certificate of the target user. The attacker deregisters the target user. The attacker waits for the target user to re-register. And then the attacker starts a login flow where the attacker basically starts a login flow for the target user and then inserts the stolen encrypted login certificate. So I will now go through each of these steps in detail. So first off, step number 1, I've already shown you this. So the attacker user reads out the registry values, pulls the server, and once the target user tries to authenticate, the attacker user steals that target user's encrypted login certificate. Step number 2 is deregister the target user. So this can again just be done with the values from the registry. So the attacker again uses these values to deregister the target user. Now the next time the target user wants to log into that computer with HYPR, there's going to be like a pop-up in the app saying, hey, you're not enrolled for HYPR login anymore on that computer. And because we assume that the target user really likes to log in with HYPR, the target user is going to basically re-register his app. And the attacker can monitor the registry, and once the target user's registry key is basically populated again, the attacker knows that the target user has re-registered, and the attacker can now reuse the encrypted login certificate. So the attacker basically starts the UAC prompt and then clicks the unlock button on the app. And this is the first request that is sent by the app to sort of kick off the entire login process. And the attacker basically changes the values marked in blue here, where the attacker basically changes the machine username to the target username and the device ID which basically identifies the smartphone to the device ID of the target user. And this is again a value that can be read from the registry. The server is going to respond with some values, and upon receiving these values, the HYPR app is going to start a biometrics prompt. The attacker is, of course, going to pass this biometrics prompt because the attacker is on his own smartphone. And the HYPR app is going to send some values to the server, and the server is going to respond with a session ID. The app sends the session ID to the server, and the server sends, and this is basically the response where the server sends back the end counter value. Now, the attacker is going to read this end counter value and compare it to the end counter value of the stolen encrypted login certificate. If it matches, then the attacker basically goes forward with this attack. If it does not, the attacker again goes back to the start of step 4 and just repeats that until the end counter matches the one of the encrypted login certificate. Now, let's say it matches. Then the attacker basically sends the stolen encrypted login certificate to the server. The server is going to respond with, okay, all good, authorization performed successfully. And the attacker is basically now logged in as the target user. So there's a few problems here. There's this repeating encryption nonce that's predictable and gets reused. So this should really be a super random value that never gets repeated. And this way it will not be possible to basically reuse a stolen encrypted login certificate. Of course, there's also the problem with the loose access control on the registry keys. So this is a problem because this really shouldn't be the case. Only the user to whom these registry keys belong should be able to read these values, not any user. And well, it's also a bit strange that login flows for other users can be started with like the attacker's biometrics basically, which is also a bit strange. But well, step 0.1 and 2 are fixed in the newest or newer HYPR versions. And well, this already brings me to the end. So a few closing words. So I looked at 3 products. There's of course more of these products that implement this, and I am also sure that I did not find all vulnerabilities in the products I looked at. So there's definitely more to be found here. If you ever run across these products, it might be interesting to have a closer look. These products allow basically that the normal user does not have to enter his password anymore or as often. But in exchange for that, there's this whole complex infrastructure that is set up where now passwords are cached somewhere and get sent over the wire. And this, of course, introduces complexity, and complexity means potentially bugs, and bugs potentially means security vulnerabilities, which may be exploited by an attacker to basically mount attacks such as the ones that I've shown before. And another point that I think is important is that now administrators, so an attacker that has basically fully compromised a computer, have now a new way to obtain and login credentials of other users. Now, this is, of course, possible anyway, but this way, the attacker can basically just impersonate what the service or the credential provider is doing. And it's, for one thing, very hard to detect and prevent because, again, the attacker is doing the exact same thing as the product. And the second thing is that the credentials that are retrieved this way are directly usable, as opposed to maybe a hash or something that might not be directly usable, depending on the Windows configuration. So yeah, I'm at the end. Thank you for your attention. So are there any questions?